Okay, practice 1 molecular dynamics. First, we have the summary of contents. In this case, we are going to talk about an introduction, methodology, results presentation, discussion and analysis of results, and finally, conclusions. Introduction. The objective of the practice was to evaluate the effect of the temperature on the viscosity of water through molecular dynamics in GROMACS. What is a molecular dynamics? Molecular dynamics is a computational simulation method that allows the analysis of molecular interactions at the atomic level. What is the goal of molecular dynamics? It's to calculate the movement in 3 dimensions of the molecules or atoms of a system through the time. This is known as a trajectory, and we are going to see the results of that trajectory as a field that contains information about the atomic coordinates of the system and how they change with respect to time. And finally, that trajectory can be used for several purposes, but in our case, it will be used to calculate viscosity. Where are we going to get the information from? It will work with the HPC of the university through the GROMACS software. HPC is High Performance Computation Center, and one of the most widespread tools for carrying out molecular dynamics is GROMACS. This is a versatile package for performing molecular dynamics simulation, the Newton equations of motion for system with hundreds to millions of particles. The university's HPC is called IPATIA. The relevance of molecular dynamics. Other molecular simulations methods only allow one stage or one state to be simulated. However, molecular dynamics provides the evolution of a system through time that is measured in picoseconds. And also, since the velocities of the atoms are considered, the kinetic energy of the system can also be calculated. Since most programs only calculate the potential energy and or the free energy.
Now we're going to talk about the methods used to run a molecular dynamics simulation, where we'll use both 1 and 4 nanometer boxes. In order to do a molecular dynamics simulation, first we need to prepare the files needed in the simulation and choose the mathematical and physical models to simulate the system. In this case, we'll use the model TIP3P for water molecules. Then we must minimize the system's potential and energy, which will help us reduce errors in the simulation by eliminating the high potential energy between atoms. After doing this, we add kinetic energy to its molecules, hence increasing the temperature and heating the system. In this stage is where Newton's equation of motion are first utilized. The next stage is known as balance or pre-production. Here the molecules are left to move freely so that the kinetic energy added in the previous stage is evenly distributed. And lastly, the production stage. This is the longest and most important part, since it is where the trajectory and viscosity are obtained by allowing the molecules in the box to move freely.
Now we will present the results of the 3 simulations. Each of them were made in a box of 4 nanometers, and each had a different temperature. Okay, so first we'll analyze the heating stage, which is the part in the simulation where it is programmed to add heat to the system so that the molecules gain kinetic energy and the temperature rises. We can see in all graphs that the time will be measured in picoseconds, which is 10 to the negative 12 seconds. On the graph on top, we have the kinetic energy measured in kilojoules per mole, and it is plotted against time. We can see that there is an increase tendency in all temperatures. For the second graph, we have the potential energy of the molecules, also measured in kilojoules per mole and plotted against time. Finally, we have the temperature also plotted against time, and this temperature is measured in Kelvin. Now, for the balancing stage, the simulation stops transferring heat to the system. This makes the molecules move freely across the box of 4 nanometers and also in the transfer of the kinetic energy between the molecules. For the first graph, we have the kinetic energy measured in kilojoules per mole plotted against time. The second graph is the potential energy measured also in kilojoules per mole against time. And the third graph is the temperature measured in Kelvin plotted against time. We can see that the functions for each of the simulation start to become more constant. Finally, we have the production stage, where molecules can move freely across the box of 4 nanometers, and this is where it's important to measure the properties. We have 5 types of energies, which is the kinetic energy, potential energy, total energy, energy due to non-polar interactions, and energy due to polar interactions. Each of them is measured in kilojoules per mole and plotted against time. Also, we have the graph for the temperature of each simulation, and this is measured in Kelvin. For the heating stage, we have that the simulation always starts in the same reference point. This is why the 3 properties have the same values in the first picoseconds. But then, as time goes by, these values start to change because the heat transfer rate is different for each system. Moving on to the kinetic energy. The kinetic energy and the temperature are related through the velocity of the molecules. A higher velocity of molecules means a higher kinetic energy, which means a higher temperature. This is shown in the graphs because the temperature, as it rises, the kinetic energy also rises. Finally, in the potential energy, we have that the force is equal to the negative gradient of the potential energy. This translates to a more negative potential energy, a more stable a system is. In the graphs, it's shown that as temperature increases, the value of the potential energy is less negative, which translates to a more unstable system. For the balancing stage, we have that heat is no longer transferred to the system. This will result in molecules finding a natural balance and the stabilizing of the 3 properties of kinetic energy, potential energy, and temperature. We can see in the graphs that the functions are more or less constant, which translates to the stabilizing mentioned before. Also, we have the same tendencies that a higher kinetic energy means a higher temperature and means a higher potential energy. Since the production stage is the most important of the simulation, a lot more data is recollected. We can see that the kinetic energy, potential energy, and temperature have the same behavior as the balancing stage. Now we introduce a new property measured, which is the total energy. This is the same as the force field, which is calculated by taking into account every single type of interaction of every single molecule in the system. Since this calculation is very complicated, we just want to look at the magnitude of the negative value. A more negative force field is associated with a more stable system. In the graph, we see that as temperature rises, the value is less negative, which means it's a more unstable system. Next, we have the energy due to non-polar interactions. This is the same as the van der Waals interactions, which decrease when the distance between the molecules increases according to the Lennard-Jones potential. We can see in the graph that when temperatures rise, the energy due to these non-polar interactions decreases. This is because at higher temperatures, the molecules have more kinetic energy, so they tend to apart themselves from each other. Finally, we have the polar interactions. This is related to the free energy, which is calculated with the formula from below. We can see that this formula has a negative value. This is very important because the more negative value of the free energy, the more spontaneous is the formation of the system. In the graph associated with the polar interactions, we can see that at higher temperatures, the less negative value, which means the less spontaneous the formation of the system is.
Finally, we have the conclusions. The first one is, although the simulation is a good approximation of the reality, it is not an exact model. This is because the simulation works with 18,000 molecules, but a mole of water contains 10 to the power 23 molecules. The second one is a limitation for this type of simulations is a computed power and time. A larger quantity of molecules means more interactions, which results in more data that takes more time. And the last conclusion is, for a more accurate approximation, it is recommended to increase the size of the box, but it is important to consider the limitations mentioned above. Thank you for watching.